first law of motion. It is also called the law of inertia. It states objects will remain at rest or in uniform motion in a straight line unless acted upon by an external unbalanced force. To understand Newton's first law completely, we need to learn about inertia first. See, this is a very large sofa. What's special about it? It's stable. It is not moving. Now go ahead and try to move it. Oh, you can't. It's not willing to move. You can't move it as it is very large. Now try to move this small stone. Good. You can move it a little bit, but you had to put in a lot of effort. It was also like it didn't want to move from its original position. Even the smaller things don't want to change their positions. They don't want to move. Even a small stone takes some effort to move. This is the first rule of physics. Things like to stay where they are. No object in this universe would start moving unless some external effort is put on it. It's like all things in the world are lazy. Now the question is, if things are lazy and they don't want to move, then how does the movement happen? The answer is that there are so many things in the universe which push and pull other things and force them to shift their positions, like you force the small stone to move. But as we said earlier that things are lazy, they would try and stop their movement as soon as the effort was removed. Well, you'll be wrong if you think like that. You'd find it very strange to accept that when a small stone was still, it wanted to stay still. But once you'd put it in motion after putting some effort, it would like to keep on moving. In reality, it would keep on moving forever and ever. But somehow it stops. But it stops not because it wants to stop. It stops moving because things in its path force it to stop. It may be due to air, or if it bumps into a tree or rough surface on the ground. But suppose there were no tree in its way, or there was no roughness on the surface, and also imagine that it does not have poles or trees in its way. The stone would never stop. It would keep on moving. It happens in outer space, where there's no air or roughness. If you kick a small stone, it'd keep on moving and would never stop. So how can we say that things are lazy? See, the small stone wanted to move forever, but it was stopped by the resistance of air, trees, or roughness of surface. It's like you moving on a slippery road. You'd keep on moving unless there was some effort put in to stop you. The same is true with the small stone in outer space. It would keep moving, as nothing came in its way. It also doesn't want to stop, as it is too lazy to do that. So now we can change the first rule of physics. Things want to stay in the position they are, to things want to keep doing what they are already doing. If things are at rest, they want to stay at rest. And if things are moving, they want to keep moving. In other words, things are lazy. So there's a lot of laziness in the universe. Physicists have a special name for this laziness. It is known as inertia. So now you understand Newton's first law of motion. Can you write it? Well, you are very much right.
Here we're going to demonstrate inertia. We have a heavy ceramic plate, got some heavy silverware, got some beautiful flowers, candle, glass of wine, and we have all this sitting on top of a silk tablecloth. So, I think you might know what's coming, but here it goes. And the trick to that is basically just do it, and do it as fast as you can, and do it straight in this direction. Straight and fast. And also practice. Maybe practice before you light the candle, but it's up to you.
Now let's move on to Newton's second law. As we know from the first law that to overcome the inertia of an object, we have to apply unbalanced force. Newton's second law talks about how fast an object would move. Well, it states acceleration of an object depends on the mass of the object and the amount of force applied. In mathematical terms, Newton's second law states that force is the product of mass and acceleration. To cause an object to accelerate or speed up, a force must be applied. The more force you apply, the quicker you accelerate. Look at these two swings. If you apply the same force on both swings, check whose goes faster. Let's first push the little kid. See? It goes very high. Now push this fat man with the same force. See, it does not go far, because it has more mass than the little kid. So the more mass there is, the force required to push the object is also greater. Let's look at the mathematical formula of the second law again. It's the product of mass and acceleration. We've already learned that if there's more mass in an object, to move it, we need more force. Now let's see this kid sitting in the swing. If we apply little force, then it goes a small distance. Now if we apply a lot more force, it goes very high. So to get more acceleration, we need to apply higher force. So now you can understand the relation among force, mass, and acceleration.
Even Sir Isaac Newton would be a fan of the fan cart. Your students will be fans too. Put the clear plastic sail in place, turn it on, and the cart doesn't move. Why not? The sail absorbs the energy of the incoming air. Take off the sail and watch it go. The air is now able to move away from the cart, causing the cart to move in the opposite direction. This inexpensive cart does everything more costly carts do, and is perfect for opening up a discussion of Newton's laws, inertia, acceleration, and action-reaction forces. A clip is included to allow the user to remove one of the batteries, so that students can measure differences in acceleration with different magnitudes of net force. Masses can be added to the cart so that students can identify the relationship between mass and acceleration. Students will love to use this cart, and it will help them understand Newton's laws of motion.
Till now, we've only learned the first and second laws of motion. Oh, you're riding a bicycle. Have you ever wondered why a bicycle moves forward? Well, it moves according to Newton's third law, which says that for every action, there is an equal and opposite reaction. To understand this, see what happens when you drop a tennis ball. As the tennis ball hits the floor, it causes a downward force on the floor. This is the action. The floor reacts by pushing on the ball the same force, but in the opposite direction. Action, reaction. Together, the floor and the ball form what's called the action-reaction pair. So now how it applies to your bicycle. When you push the pedal, the parts of the tire which touch the ground push it backwards. The ground also pushes the tires forward with the same force. So the parts of tires and earth form a pair of action and reaction. So what happens to the earth when your tires are applying force to push it backwards? Huh? Oh! Nothing happens to it, since the earth is very big as compared to your bicycle. The force applied by your tires does not move it backwards, but force applied by the earth pushes your bicycle forward. So now you understand Newton's third law. Yep, the tennis ball is the right example. The ball and the floor are creating a pair of action and reaction.
Could just pretend to be with her all day. Remember the feeling when you first held hands today. Imagine her in your favorite white dress, smiling at you as if she thinks that you're the best. She tells you and me, sitting on a tree, K-I-S-S-I-N-G. You tell her, baby, hear me out. Will you marry me tonight? We're in this make-believe reality. Just you and me, make-believe reality, but maybe this is killing me. Make-believe, 'cause tonight she holds you tight.
Okay, we're going to take a look at Newton's third law, just using a balloon. We blow up the balloon now has air pressure inside. Why is the balloon not going anywhere?
Because you're holding on.
I'm holding on to it. Is any air escaping the balloon?
No.
No. Now, if I let this go, what's going to happen?
Air will escape.
Air is going to escape and the balloon will fly around. All right, so we let it go, and it flies away. Now, Newton's third law states what? What were the two words? Action, reaction. What's the action in this case?
Air escaping.
What's that?
Blowing up the balloon.
No.
Letting go.
Air coming out. Now, does air, what happens here?
Propulsion. Goes the other way.
What's the air pushing on?
Air.
Air. Does air have mass, have weight? Let's use mass, not weight. Does air have mass?
Yes.
Yes. So the air coming out pushes against the air that's here. What's the reaction then?
Flying
The
around.
balloon flying away and flying around. In outer space, is there any air to push on?
No.
No. In outer space, what happens? The thrust of the rockets, the thrust and the force of the engines going out is the what?
Action.
Action. The reaction is the rocket
Going away.
going the other way. Okay? Here we go. All right, we got. Okay.